SagaChain uses transaction execution sharding as the means for increasing throughput capacity with an increased number of shard chains. Each shard chain executes non-conflicting transactions in parallel with all other shard chains independently. A transaction is non-conflicting if the data modified in the transaction on a given shard chain is not modified simultaneously on any other shard chain. The unit of data managed by SagaChain to create non-conflicting transaction ordering is the SagaChain account object instance. A transaction is considered non-conflicting if the account objects that are modified as a result of the transaction's execution are not modified by any transaction on any other shard chain simultaneously. Conflict elimination is accomplished through the concept of account object ownership by an individual shard chain from the set of currently executing shard chains. An account object may be in the following states with respect to the set of SagaChain shard chains owned, unowned, and read-only. The following rules are enforced. A transaction may modify an account object only if the shard chain executing the transaction owns the account. A transaction may read an account object on one or more shard chains only if it is unowned by all shard chains and designated read-only at the time of the transaction. An unowned account may not be used in a transaction on any shard chain at any time. The objective of the account negotiation algorithms is continually distributing the account ownership across the available shard chains to maximize the opportunity for independent parallel execution of transactions on separate shard chains. A higher level of parallelization equates to a higher throughput capacity over the set of shard chains. Composability in blockchains is currently understood to mean combining multiple smart contracts such that one smart contract calls one or more other smart contracts during a transaction. A common case is a DeFi smart contract that makes calls to one or more token smart contracts. When calling between smart contracts, the state of the smart contracts must be known by each node executing the smart contracts. From a data sharding viewpoint, there are various approaches. One approach termed L1/L2, where L1 and L2 refer to layers of blockchains. Data on separate L2s are not synchronized with each other, such that a smart contract on one L2 that makes calls to a smart contract on a different L2 must synchronize via a L1 common to both L2s or some other similar mechanism. This has been termed cross-shard communication. Composability with SagaChain is a natural extension of its inherent object-oriented design. All message passing is via using an object ID as the reference to an object. An object is said to be owned by account object, and that ownership may change over time. The change in account ownership does not change the object ID reference, such that a transaction or another object messaging that object will succeed regardless of the current account owner. Account negotiation enables dynamic composability in a transaction and data sharded environment while avoiding cross-shard communication, L1/L2 constructs, and other similar mechanisms. SagaChain replaces the cross-shard data problem with per-shard account ownership management and transitions. The account negotiation cycle consists of 5 stages, of which the first 3 are discussed here. Account usage identification per transaction, account ownership request creation, account assignment and release negotiation, account pending transfer designation, account transfer completion. The last 2 steps are part of ownership state management given the result of the account negotiation algorithm. All state data is represented as objects consisting of a set of data fields in SagaChain. All objects are referenced by globally unique 32-byte addresses. SagaChain uses a meta-class model. This means that objects are instantiation of classes, and classes are object instantiations of classes. The class of a class is distinguished as a meta-class, a class that creates a class. All objects inherit from a single root object, SPC class object. An account object is an instance of a SPC class account or subclass thereof, and is the organizing data concept for managing transaction execution, parallelization across the set of shard chains. All objects reference other objects using their unique 32-byte addresses. All non-account objects are owned by a single account object designated by an account object reference field. which may change over the course of a transaction execution. An account object contains an object if the object is reachable by following object references directly or indirectly from the account object's state, and that the referenced object's account ownership field matches the account object's unique 32-byte address. An object instance may be owned by an account but not currently referenceable from the account object directly or indirectly. An account is designated as modified if the account object state changes during the course of a transaction execution, or if any object that is owned by the account changes state. For each shard, a list of account tuples, each tuple consisting of an account ownership request list and account read-only request list, is input, where the ordering of the list of tuples is by preference from the shard leader. The list of modified accounts and read-only account in an individual tuple request from a shard are mutually exclusive. The outputs is a list ordered by shard of accounts assigned to and released from each shard, and a list of accounts that are read-only. Pending means that the account negotiation has determined account ownership acquisitions, releases, and read-only state for the respected outputs, independent of the current ownership state of the account over all shards. An account may not be assigned pending acquisition and pending release for the same shard. An account may not be assigned pending acquisition and pending read-only. An account may be assigned pending release and pending read-only, such that the account becomes read-only when it is released from the current owning shard. The algorithm aims to maximize the number of account tuples that are satisfied without conflicts across the set of shards by the account assignments. Another objective is to minimize the number of accounts whose ownership is transferred between shards. Finally, it seeks to maximize the total value of the tuples satisfied by the account assignments, given the V function. The search space consists of the list of tuples from each shard and the number of shards. A tuple can only be chosen if it does not conflict with any of the already chosen tuples for any account. 0 or more tuples may be chosen for each shard from its list of tuples. A given account may be used either as uniquely assigned to a single shard or in read-only form across one or more shards, but not both, with one exception. A given account may be used both as uniquely assigned and modified, and as read-only in 2 or more tuples, provided that all such tuples are requested from a single unique shard. A solution may be verified in polynomial time, indicating that this is an NP problem. The search space is the total number of tuples input, which has a maximum of the number of shards multiplied by the length of the tuple list allowed per shard. The set packing problem consists of finding completely disjoint subsets from a list of possibly overlapping subsets. An assignment of tuples to shards such that the modified accounts in each tuple are unique with respect to all other shards is a form of an integer set packing problem. That is, a modified account may only be assigned to one shard at a time. The set cover problem consists of finding a set of subsets from a list of possibly overlapping subsets such that each value in each subset is present in one or more subset accounts that are read only in each tuple, may be seen as part of the set cover problem, such that an assignment of tuples to shards may include read-only accounts common to multiple shards from such tuple assignments. As a departure from the set cover problem's requirement that there is a full covering of all values in each subset, an account assignment solution does not require all read-only accounts are assigned. The SagaChain account assignment protocol does not specify the algorithm the account assignment negotiator uses. A node, when elected as the account assignment negotiator, may employ any algorithm to find a solution. A rational algorithm will seek to maximize the above objectives such that SagaChain transaction throughput is maximized and transaction latency is minimized. Maximize transaction throughput and minimize transaction latency optimize the utility of SagaChain for general use, which results in increasing demand for SagaChain transactions and increasing purchasing power of SagaCoin. Increased purchasing power benefits all node operators. The SagaChain assignment algorithm, referred to as PSAA for the remainder of this document, uses a randomized, online, greedy, directed search traversal algorithm over the set of shards. The algorithm consists of multiple runs, where each run is bounded by the number of shards, and the total number of runs is bounded by an arbitrary iteration count. The PSAA does not claim to find an overall optimal solution, as that would require exhaustive search. Instead, the PSAA claims that it finds an optimal solution from the set of solutions that it generates in a bounded number of CPU cycles. Optimal solution in this context is with respect to maximizing the objectives. The following is a high-level description of the PSAA input assumption. The ordering of account tuple requests from each shard is from the highest value to the lowest value for each shard, respectively. The definition of value is specific to each shard leader, but it is expected to be a combination of the number of transactions satisfied by a given tuple and the transaction fees that would be earned by those transactions. The algorithm is implemented as a search over the set of potential vertices, where each vertex represents an assignment of tuples from a shard, such that a directed graph is formed where the leaves of the graph are possible assignment solutions for the set of tuples over the set of shards. The algorithm iterates over the following until further progress towards a maximum valuation is not made after n tries, bounded by m maximum iterations. The current maximum valuation of tuple assignments is returned. For each iteration, the set of shards are randomly shuffled in order at the beginning of the iteration. A dummy empty vertex is created as the starting point. The random shuffled shard list is iterated over. For each shard, the list of passed-in tuples is iterated to generate 4 proposed new child vertices in the graph from each current vertex using the following 4 sets of criteria individually. Where there is an existing set of tuples resulting from iterating over the previous shards in the current randomized ordering of shard for this iteration. For each account in each tuple, the following criteria giving priority to modified versus read-only accounts is applied, adding as many tuples as possible to the new vertex, while also removing any conflicting tuples where required. Previous read-only over modified and previous modified over read-only, modified over previous read-only and read-only over previous modified, modified over previous read-only and previous modified over read-only, previous read-only over modified and read-only over previous modified. For each shard iteration, the top 4 vertices are chosen as input to the next iteration with the next shard in order. This results in 16 choices per iteration and 4 output vertices. The concept of top vertices is determined by a heuristic weighting function applied over the 16 possible vertex choices. At completion of iteration over shard list, the maximum of the 4 vertices returned is compared against the current maximum. If greater, then progress towards a maximum is ongoing and a fail count is reset. If not, the current fail count is incremented and compared with a max fail count value to bound the search if further progress is not made over the random shuffle of accounts. The algorithm is further bounded by the maximum trial iteration count. On completion of the algorithm, the final vertex is the best tuple assignment solution within the 2 iteration bounds. For each vertex in the assignment algorithm graph, there is a set of tuples that have been assigned containing non-conflicting accounts with each other, and a list of tuples that are unassigned due to conflicts with the current set of assigned tuples. For each account from each new tuple introduced from a shard's tuple list, the account may be a modified account or a read-only account. Similarly, for each account in each tuple in the current list of non-conflicting tuples, the account may be either modified or read-only. The accounts that are in a tuple in the current list are termed previous, thus previous read-only and previous modified, while the new accounts from tuples potentially being added are termed simply modified or read-only. There are 4 separate criteria applied with respect to each existing vertex. The criteria give priority either to the accounts that are previous modified and previous read-only in the existing tuples list, or are the new modified and read-only accounts from new tuples to be added. Each criteria determines if the new tuple can be added to the set of non-conflicting tuples. As part of applying the priority ordering, an existing tuple that was previous in the non-conflicting tuples list may be removed and placed in the unassigned tuples list. Additionally, tuples that were previously conflicting and are in the unassigned tuples list, as a result of the priority criteria, may now be non-conflicting and may be added to the non-conflicting tuples list. The names of the 4 criteria are self-explanatory but written out below for completeness. Previous read-only over modified and previous modified over read-only. If a modified account in a new tuple conflicts with an existing previous read-only account, the previous read-only account takes precedence and the tuple may not be added. If a read-only account in a new tuple conflicts with an existing previous modified account, the previous modified account takes precedence and the tuple may not be added. Modified over previous read-only and read-only over previous modified. If a modified account in a new tuple conflicts with an existing previous read-only account, all tuples in the non-conflicting tuples list that include the read-only account are removed and added to the unassigned tuples list, and the new tuple is added to the non-conflicting list. If a read-only account in a new tuple conflicts with an existing previous modified account, all tuples in the non-conflicting tuples list that include the modified account are removed and added to the unassigned tuples list, and the new tuple is added to the non-conflicting list. Modified over previous read-only and previous modified over read-only. If a modified account in a new tuple conflicts with an existing previous read-only account, all tuples in the non-conflicting tuples list that include the read-only account are removed and added to the unassigned tuples list, and the new tuple is added to the non-conflicting list. If a read-only account in a new tuple conflicts with an existing previous modified account, the new tuple is added to the unassigned tuples list. Previous read-only over modified and read-only over previous modified. If a modified account in a new tuple conflicts with an existing previous read-only account, the new tuple is added to the unassigned tuples list. If a read-only account in a new tuple conflicts with an existing previous modified account, all tuples in the non-conflicting tuples list that include the modified account are removed and added to the unassigned tuples list, and the new tuple is added to the non-conflicting list. In addition to the priority criteria, the general rule that a modified account may only be assigned to one shard at a time is enforced. A tuple is only added to the non-conflicting list for a given criteria if all accounts pass the criteria in the tuples list. Each shard leader is responsible for creating the list of account tuples requests for each round of the account negotiation consensus protocol. A shard leader is not required to make any account requests in a given round. The intent of a tuple list of accounts is that the set of accounts requested for ownership and read-only enable one or more queued transactions to execute. The execution of a transaction involves at a minimum one account terms the primary account and 0 or more secondary accounts. The transaction header must identify the primary account and optionally may identify the secondary accounts. There isn't a requirement that the transaction message the primary account or any objects contained by the primary account. To participate in the account negotiation consensus protocol, a shard leader must generate a list of tuples of accounts and rank them in order of a value measurement, providing the ranked order from highest value to lowest value to the account negotiator leader. The value measurement is a local matter and may vary across shard leader nodes. Value may be measured in the number of transactions that may be executed by a given tuple of accounts and the amount of transactions fees that would be generated. Other value measurements are possible. The account negotiation consensus protocol does not have visibility into the value measurement that generated the ranked ordered list of tuples from each shard leader. There are two means to determine the accounts needed to execute a given transaction: explicit statement in the header of the transaction and a trial execution of the transaction. If a list of accounts is provided in the transaction header, then the shard leader may directly create a value measurement for a tuple comprising the listed accounts. A shard leader performs a trial execution of a received transaction capturing two output account lists, accounts that are modified, and accounts that are read but not modified. It is likely that multiple transactions have secondary accounts in common, with only the primary account varying. A reasonable organization of account tuples would be to combine tuples that have all secondary accounts in common, but varying primary accounts. The account request then consists of the ranked list of tuple outputs. The tuple output is submitted to the account negotiation consensus protocol as the request for accounts by the shard leader. Transactions are submitted to SagaChain by clients either to a single node or multiple nodes. The transactions are gossiped to the shard leaders for inclusion in blocks. The account ownership rule requires that a transaction can only execute if the accounts involved are either owned by the shard or are read-only across all the shards. As described above, the transactions either list the accounts involved in the transaction header, or the transaction is trial executed to identify the accounts. For all trial executions, to realize the goal of increased throughput capacity with increased resources, the occurrence of redundant trial execution of transactions by multiple shard leaders must be minimized. The alternative, where multiple shard leaders trial execute a common set of transactions, tends to limit the real throughput to the performance of a single leader. In other words, the parallelization of execution sharding is lost due to the bottleneck of the trial executions. Minimizing redundant trial execution is the goal of every shard leader. The algorithm or algorithms used to determine the set of transactions to trial execute for any shard consensus round is local to the shard leader and transparent to both the account negotiation consensus protocol and the local shard consensus protocol. Various alternative algorithms may operate simultaneously on independent shard leaders. Batched queuing delivers a queue of fresh transactions to a transaction selection algorithm. The algorithm proceeds as follows. Place all transactions that identify the list of accounts needed in the transaction header in an output queue. Sort the remaining transactions based on the primary account identifier into 3 lists. Transactions that the primary account is currently owned by the shard. Transactions that the primary account is currently owned by a different shard. Transactions that the primary account is currently unowned. Sort list 1 by transaction fee, using gas unit calculation plus any additional fee. Trial execute list 1. For each account list output, add to the output queue. If a sufficient number of transactions have been queued, stop. Sort list 2 and list 3 by transaction fee. Randomly select from list 2 and list 3 and trial execute the selected transaction. For each account list output, add to the output queue. When a sufficient number of transactions have been queued, stop or stop if the remaining lists are empty. The output queue is sorted to create the tuple request list as described above. Any account tuples that have full account ownership coverage currently by the local shard have their associated transactions queued to a ready queue for the next shard proposed consensus block from the shard leader. The remaining transactions are queued waiting for one of the following outcomes. All of the accounts in the tuple become owned by the shard or are read-only, placing the associated transactions in the ready queue for inclusion in the next shard proposed block. Any transaction executed on a different shard and received in a shard consensus block is removed from the transaction queue. The random selection is intended to minimize the trial execution redundancy among the shards. Although it is possible to implement out-of-band communication between shard leaders to further reduce trial execution redundancy, such communication paths are not part of the SagaChain decentralized consensus protocols. No out-of-band communication protocols have been implemented at this time. It is possible for a shard leader to maintain local historical knowledge of account relationships in various transactions to further prioritize the order of trial execution of transactions. SagaChain does not maintain or use any historical knowledge at this time. Any such implementation changes would be local to the given shard leader and are opaque to all other shard leaders and nodes in general. The PSAA does not claim to find an optimal solution for each cycle of the algorithm. The claim is to find a solution among the range of generated possible solutions that is optimal in some sense within those solutions, bounded in time and with bounded resources. The selection of the optimal solution is evaluated with respect to the output objectives. Underlying the output objectives is a conjecture regarding the relationship of accounts across multiple transactions. Given a single transaction between two or more accounts, the accounts involved in the transaction are completely random. There is no means to predict the accounts identified. If all transactions are completely independent of each other, then, given an entire list of transactions, the accounts involved in each transaction are unpredictable and completely random. The PSAA will create a solution that is valid and optimal given the set of generated solutions. The Prasaga social relationship conjecture, or simply Prasaga conjecture, proposes that given a set of submitted transactions over a given limited time duration, there are subsets of accounts satisfying subsets of the list of transactions, such that the subsets of accounts are completely overlapped and in common. The Prasaga conjecture states that over a limited duration of time given a subset of accounts, there is a higher probability that they are used repeatedly in a set of transactions arriving during the period of time than a random set of accounts. Therefore, by assigning the accounts to a given shard, the set of transactions may be executed when they arrive without additional overhead of moving ownership to the given shard from other shards or from an unowned state. The justification for this is a social justification. Transactions are submitted by people, or possibly other machines, to accomplish a goal. Over a limited time duration, multiple transactions are likely to be submitted related to that goal. As an example, consider shopping in a mall or at Amazon online. A shopper performs a transaction with a given checkout counter at a store. This involves the shopper's account and the store account. There is a higher likelihood that a subsequent transaction will involve the store account over the next duration than a random account. There is also a lesser probability that the shopper's account will be involved in transaction with the store account, but also greater than a random account. The stock markets and related markets can be seen as either purely random walks in stock value or non-random walks in stock value. All of the modeling, hedge funds, quants, etc., are based on the belief of non-random walks, enabling leveraging some level of predictions. Otherwise, a random coin toss would be just as effective.